Hello class, today we are going to work on drawing Lewis structures for covalent molecules. We're going to start with things that typically only have single bonds. So in the past, when we were looking at ionic compounds, we drew Lewis structures for single atoms and we showed the transfer of their electrons from one atom to another. But when we are looking at covalent bonds, we know that they are dealing with the sharing of electrons. So I first wanted to open up by looking at some diatomic elements. If you remember that word diatomic, it's been a while since we've seen that, but diatomic refers to an element that bonds to itself, means it only has two. There are 7 diatomic elements. We have H2, F2, Cl2, Br2, I2, O2, and N2. All those things bond to themselves naturally in nature. So all the hydrogen that we're breathing, all of the oxygen and nitrogen that we're breathing from the air all exist in this diatomic form. So let's draw the Lewis dot for fluorine. We know fluorine is in group 17 or 7A if you're looking at your periodic table, which means it has 7 valence electrons. And we know it's going to exist naturally with a second fluorine. So I'll draw 2 of each. Now, you'll notice that each fluorine needs 1 extra electron in order to have a complete valence shell and to satisfy the octet rule. Now, if we tried to do it the way we did before with our transfer of electrons, you end up with one of your fluorines having a stable octet and the other one now being down 2 electrons. So we know that this is not something where a transfer of electrons will work for us. We need to share electrons. So each of these, if we circle them together here, are going to be shared between each other. So if I were to cover up the F on one side, you'll see that the F on the left now has 8 total valence electrons, including the one that was shared. If I were to do the same on the other side, same deal, you see 8 total valence electrons, including the one that is shared. Now, we don't circle the electrons typically when we draw. We end up using a line to represent our electrons that are being shared. In reality, we know that there is, in fact, an electron at each end of that line bond. Now, we don't need to draw in those dots there. I just highlighted them so you can see that one line does, in fact, represent 2 electrons. But really, the best way to just draw this is the way that we see it here. If I look at some other things like hydrogen, same deal. Hydrogen has 1 valence each. We know it only wants 1 more valence electron because it only has an s orbital in that first energy level. So if we just connect the 2 together, we have made our covalent bond. So in summary, you'll see that a lot of these follow the same pattern. We've already drawn our F2, we've seen I2. What's interesting is Cl2, Br2, and I2 are all in the same group as fluorine. So they're all going to bond the same way because they each have 7 valence electrons to start. And you probably could have made that prediction on your own. But we'll see that each of them has 3 sets of lone pair electrons and 1 single bond between each of them. Now, when I go to do oxygen, oxygen only has 6 valence electrons. So what's interesting about this is that if we were to share 1 set of those and cover up one of my atoms, we only end up with 7 valence electrons. That's not good. That means we end up having to share an additional 2. So if I were to draw this a little nicer, this is going to lead us into a discussion about the different kinds of bonds that we have. So if I share 2 sets total, now each atom has 8 electrons. I have 2, 4, and then at the end of each line, that makes 6, and then the other end of the line makes 8. So in total, each oxygen still ends up with the correct number of electrons that it needs, but it has to share a little bit more than normal. When we go to do nitrogen, nitrogen has only 5 valence electrons, and you'll see that if you were to work it out, this one ends up having what's called a triple bond. So you see this unique feature of double and triple bonds that we're going to talk about a bit more in our notes. And we will go over a better process for how to approach these problems as we continue. So in a covalent bond, we know that electrons are shared so that atoms can achieve a full energy level and satisfy their octet rule. When we previously talked about differences between ionic and covalent compounds, we know that ionic compounds are typically formed between a metal and a nonmetal, whereas covalent compounds are formed between 2 nonmetals. Something you have to remember is that nonmetals have a higher electronegativity than other atoms such as metals. Since they have a high electronegativity, they're really good at attracting electrons towards themselves. So since they all want to gain electrons, donating electrons to each other is not something that's going to happen. They're going to have to share because they both are greedy and they really want to gain some electrons in some way. When we draw Lewis structures, you'll find that one atom tends to be in the center. It's called the central atom. It's usually the one that wants to gain the most electrons. So carbon is usually a good candidate for a central atom because it has 4 valence electrons and it needs 4 more to get to 8. We also know that it's typically the least electronegative atom that ends up in this center. The one exception to that is hydrogen. Hydrogen is fairly low in electronegativity, but it can only ever make a single bond because it's limited to that 1s orbital or that first energy level. We know we can only have 2 electrons in the first energy level, so hydrogen will never want to be a central atom because it can never get to 8. It's not very good at sharing more than 2 electrons with anybody. When we talk about electrons that are being shared, we refer to them as a bonding pair or a bond line in a Lewis structure. If we're talking about electrons that are not shared, we refer to them as a lone pair. So here's a depiction of NH3. This is just one version where they show the electrons between each other, but if we were to draw it with lines, we have one line in between each N and hydrogen pair that we have, and then the lone pair exists only on nitrogen, but it's hanging out just as a set. So even though it's a pair, it's alone because it's not part of any sharing that's occurring. When we're talking about the different bond types, a single bond is formed by sharing 2 electrons or 1 pair. In terms of strength and length, we also know that single bonds tend to be the weakest type of covalent bond when compared to the double and triple bonds. It is also the longest of the different bond types that we have. When we end up with a double bond, we have 4 electrons being shared in total. With a triple bond, we end up with 6 electrons being shared in total. The triple bond ends up being the shortest, but it is also the strongest overall. The double bond, that means, is somewhere in between the single and the triple bond in terms of bond length. So we use 1 line to represent a single bond, 2 lines for a double bond, and 3 lines for a triple bond. And here's just a representation going back to those diatomic elements we were looking at before. Definitely feel free to pause the video if you need to and take a look at those things. Also, for some reason, looks like we're missing some electrons on this oxygen. The oxygen should have, each of these oxygens should have an extra electron here. I'm not sure why that happened. So the reason we're looking at these is because a lot of the molecules we encounter in the world are organic molecules, things that form covalent bonds. Uh, the things that we'll draw in this class to start are fairly simple, but organic molecules can be a little more complex. An organic molecule is normally made up of carbon, oxygen, hydrogen, and nitrogen. Sometimes phosphorus and sulfur are there too, but you'll see them every once in a while. Vinegar is a good example of a organic molecule. It has a formula of CH3COOH. And typically, organic molecules have multiple atoms with long chains of carbon and hydrogen in them. If you're trying to figure out the structure of something like this, you would use the order that the elements are written as a guide, but we typically ignore the hydrogens first. You'll see when we start drawing Lewis structures in a little bit that we will have a skeleton that we're going to form. A good skeleton for this vinegar is to start with the C, attach another C, and then attach my O's. Typically, when you see oxygens, they don't like to bond directly to other oxygens. So if you see two oxygens next to each other, what it really means is that both of them are going to be sticking off of the neighboring element. But typically, carbon is always in the middle, and oxygens will branch off of other atoms. We also know that carbon typically doesn't like lone pairs. Now, this section here on organic molecules, we'll see more in practice a little bit later, but it is good to know if you're going on to a general chemistry class in college or an organic chemistry class. If you're doing any sort of science major in the future or health major, they'll likely make you take an organic chemistry class. So you'll have to get used to seeing things like that. And then here's the structure for vinegar, and that the process for which we determine this we'll cover in our next video, but it is just good to see how those things are formed. You can see that this first C is the same as this one here with 3 hydrogens sticking off of it. This second C has each oxygen sticking off of it, and then this particular H is bonded to the oxygen. As we get more practice with these things, it'll become a little more intuitive, but as I said, it's just good to see for right now. In our next video, we're going to do a couple of practice problems, specifically with just how to draw Lewis structures. See you in the next one.